Hey guys, in section 11.9 we're going to take a look at electron arrangements, and what this really is coming to terms with the notation that chemists and even physicists use to write the way that atoms fill electrons, or another way to say it, that's the notation we use to express where in space atoms keep their electrons. There is a hot, what do you call it? You can click on this. Click for OpenStax notes. If you click on that, you can open the link, and it will take you to this web page. And if you think this is something that would be helpful to you, by all means, um, you can scroll up and take a look at this. And it's just another way to get the same thing that I'm giving you here. And so what we do is we start with these two pictures, and I'd like to start with the picture on the right first. This is a bit of a graph. On the x-axis, we've got the principal shells, so n equal 1. This would represent the first ring. Maybe in another class you learned about how electrons are arranged on rings around the nuclei. We're going to fine-tune that a bit. This would be the second ring or second principal shell. Third ring, fourth ring, fifth ring, and so on and so forth. One of the things you may have learned is that the first ring can hold 2 electrons, the second ring can hold 8 electrons, the third ring can hold 18 electrons, and the fourth ring can hold 32 electrons, and we'll see sort of how that plays out today. I guess we can see it right now. Each one of these boxes holds 2 electrons. You learned in the last section that one of those electrons has to spin up and the other electron has to spin down. So that's why the first ring holds 2 electrons. There's only one box there. It's also worth recognizing that this is the 1s orbital. It's the lowest energy state. The y-axis is energy. Now, in the same way that water wants to flow to the lowest point, electrons want to drop to the lowest available energy. So this ground state is where every electron wants to be. But let's go back to the rings. The first ring can hold 2 electrons because there's one box there. Now we go to the second ring. The second ring has 2s and it has 2p. And since there are 4 boxes, 1 for s and 3 for p, and each of those boxes can hold 2 electrons, 2 times 4 gives us the 8 electrons, right? This is also the reason that 8 is a magic number in chemistry. You may recall months ago we learned that when an atom has 8 valence electrons, it's stable. Well, where does the number 8 come from? It seems to be pulled out of a hat, but it's not. It comes from the fact that these s and p orbitals are always going to be on the outside of an atom. And since there's one s orbital and 3, well, technically it's 1 p orbital with 3 sublevels, that's where this business of 8 valence electrons comes from. On the third ring, we now have 1 box for s, 3 boxes for p, 5 boxes for d. That adds up to 9 boxes in total. Each box holds 2 electrons, and that's where the 18 comes from. And then you can count the boxes, multiply by 2, and you get the 36 for the fourth energy level. The idea here, as I just stated, is that electrons want to get into the lowest energy orbital possible, which means that the first electron is going to go into 1s, and the second electron is going to go into 1s, but after that, the 1s orbital is full. Each box only holds 2. After 1s is full, the third electron, if there is a third electron, is going to try to get into the 2s orbital. And so is the fourth electron. But once the third and fourth electrons fill up this 2s orbital, we can't put any more into it. We have to go to the next available lowest energy, and that's 2p. And now we can put in 6 electrons here, right? After we've filled up 2p with 6 electrons, then we move up to the 3s orbital, fill that up with 2 more electrons, and you just keep climbing up this ladder, so to speak. Each time you fill an orbital, you move to the next available orbital that's at the lowest energy. Now, remembering the order of these can be a bit of a trick. In other words, remembering 1s is easy enough and 2s, but after a while, you say, how do I remember when I'm getting up into here, the order I fill these things in? That's where the chart on the left side comes in. You simply follow the diagonal arrows. And what that means, it doesn't say it, but you would start right up here, and you would fill the 1s orbital first with 2 electrons. And then you follow the arrows, and the arrows are supposed to loop back on each other. So you follow this, and then it kind of loops back to this point, so that after filling 1s, you fill 2s, then the arrow loops back, then you'd fill 2p, then you'd fill 3s, arrow loops back, then you'd fill 3p, 4s, 3d, 4p, 5, and you just keep filling in this order until you get to 7p. And what's happened at 7p, as we'll see in a moment, is that you've reached the end of the periodic table. Now, one thing that we haven't talked about yet are excited states. I think I'm going to hold off on that. I want you to learn how to fill these in order, and then we can start thinking about excited states afterwards. One of the things that people struggle with sometimes is recreating this chart from memory. It's easy enough to look at when you see it like this, but how do you recreate it from memory? The idea here is to see the patterns. The first column is always going to be an s orbital. Second column's all the p orbitals, third column's all the d orbitals, fourth column's all the f orbitals. Then go by rows. All the 1s are here. You'll notice there is only one s. There is no 1p, there is no 1d, and there certainly is no 1f. Then you go n equal 2. That corresponds to this n equal 2 down here, right? There's a 2s and a 2p. So here there's a 2s and a 2p. Then we go to n equal 3. For n equal 3, there's a 3s and a 3p and a 3d. So 3s, 3p, 3d, and you just keep going that way. Once you get to 4, you reach the 4f, and then 5f, and then it tails off again. There is no 6f. Technically, we could have a 6f if we got into excited states, but we're not going to do that. So we're going to say there's no 6f, and then there's no 7d, right? So it kind of makes a sort of a triangle that's on its side. Is there an 8s? Well, this video is being recorded in May of 2020, and as of today, I'm not aware of an 8s, but as chemists continue to make more and more new elements, or synthesize more and more new elements, maybe if you're watching this video in a few years, we will need to add an 8s box here. Another thing to be aware of is that the numbers start in order. So we go 1s, 2s, 2p, 3s, 3p, 4s, but then we go backwards. We go from 4s to 3d, and then back to 4p. Why does it go 4 to 3 to 4? And you'll notice it gets even worse than that. Eventually it goes 6, 4, 5, 6, 7, 5, 6, 7. Why is it jumping around like that? And the detailed answer is a little complicated, but basically, this might be the best way to think about it, is that you want to fill them in order from lowest to highest. And so after 4s, the next lowest available energy level is in fact 3d, and then 4p, and then 5s, but after 5s, the next available energy level, the lowest energy state, is 4d, and then 5p, 6s, 4f, and so on and so forth. And so that's the reason it fills in kind of a goofy way, is that electrons are always trying to get into the lowest available energy state. Here's another way to see this on the periodic table. There's kind of a lot going on here, but what you want to take away, the big thing to take away from this picture, is that the first two columns of the periodic table make up the S block of the periodic table. Now I know helium's over here, but for the purposes of these orbitals, helium really is over here in the S block, right? So the first two columns make up the S block. The transition metals in the middle make up the D block. All of the representative elements over here on the right side make up the P block, and the bottom two rows make up the F block. You can use this periodic table in the exact same way that you use either of these two pictures to help you know the order that these things fill in: 1s, 2s, 2p, 3s, 3p, 4s, 3d, and so forth. And you would do it just by following the arrows. So after 1s, you got to go over here and fill up 1s. Then you come back, reading left to right, top to bottom, same way you read a book. You fill up 2s. After that, you have to go over to the 2p orbital. After that, the 3s. Follow the arrows to 3p, 4s, 3D, just following arrows, 4p, 5s, 4d, 5p, 6s. Now follow the arrows down to 4f, go to 5d, so we're at 5d, 6, and you can follow these arrows, 5f, 6d, and 7p, until you run out. You get to the end of the periodic table. And that's why I said up here, we stop at 7p. You'll notice that isn't shown here because this one stops at 5d, right? In other words, this picture on the right side stops right here, but there's all these other levels that could have been added to this picture. We stop at 7p because that's where the periodic table ends. And those comments I just made about 8s are referring to the fact that as of May 2020, there are no elements in this part of the periodic table. In other words, there is no 8th row of the periodic table, at least not yet. So this is where I'm going to wrap up the first video for this section. I'll make another video for this section, and we'll go into detail on the notation that we use as we fill up these orbitals for different kinds of atoms.